So in the first video that I did about boilers, I really sort of emphasized the need for proper design and calculations for a stainless steel boiler, or any boiler for that matter. And there's a very good reason for that. For the most part, and in fact every failure that I've seen both in industry and in my home workshop, although there weren't that many in my home workshop thankfully, was due to a poorly designed weld or a poorly prepped weld. The welding part is actually the easiest part of the job. So 9 out of 10 times the failures come from a poorly designed weld or a poorly prepped weld. So that first video is actually quite important. This video is a very easy video. It just tells you how to put the thing together and weld. Now, in any boiler design or any critical design, you actually need to have a procedure qualification record. Now you can get these from the sort of the big codes, the welding codes. Every one of them have got a sort of form that you can fill out. And all that it is it's just a roadmap for how to weld. It gives you the different types of weld, and then you fill in the form and just stick to this for your boiler welding. My boilers are very, very simple. They only have 1 or 2 different types of weld. And what I do is I fill this out and I give this to the boiler inspector. And it is very, very, very simple. The first thing to do is set your TIG argon gas. And I specify a flow rate of around 9. Now, that could be a little bit higher, could be a little bit lower. 9 seems to work for me because I'm in an environment where there's no sort of gusts of wind or anything like that. And let me just show you my, and this is my horizontal mill that I restored while we walk past that. Here's a sort of tool grinder that I made a long time ago. This works really, really well. And then right at the back of my workshop, I store the argon gas tank. And all that it is a tank, which is a rental in my neck of the woods. It has a regulator, and the regulator just steps down the pressure, and then you have your gas flow over here. This is typically set to 9, so around about there. And depending on how much gusts you have in your workshop, you might want to go a little bit higher. For me, 9 works really, really well. The tube runs sort of at the back of everything. Oh, my nice little horizontal milling machine runs at the back of the table, out of the way. Just make sure that there's no nipping. My welder is nicely underneath the bench, and I will get to all those fancy knobs later, but it's relatively simple. And for the most part, you're only going to use 1 knob anyway. And the reason why I do that is because I want anyone to be able to weld my boilers. So I don't really use a lot of the fancy stuff on this very cool welder, I must add. Right at the end of the video, I will show you exactly what each little knob does and their specific application, but I'll do it from a first principles. I'm not going to worry about the fancy names and stuff. Right, let's get back to this table. So if you're going to be doing any sort of TIG welding, you really do need a auto darkening helmet. Seriously, don't bugger around with the other helmets. Get yourself an auto darkening helmet. It is really worthwhile. What happens often is when you buy one of these helmets, you get it out of the box and you strike an arc and you immediately blind it because the auto darkening doesn't work. Now, don't be angry with your tool supplier, and don't be angry with the quality of the helmet. It's actually not the helmet, and it's definitely not the tool supplier's fault. You see, what happens is inside this filter, there's a little 3.7 volt battery, one of those sort of coin batteries. And they tend to run flat, especially if they've been in a box for any sort of amount of time. And also in your home workshop, if they're stuck in a dark corner, they're not going to charge. This little solar panel over there charges that battery and keeps it fresh. But look, don't send your helmet back if that battery is dead. What you do is you just take this helmet, you stick it in the sun for 1 or 2 hours, and Bob's your uncle. It'll work just fine. Unfortunately, I've had my helmet for many, many years, so that battery has long since died. It only has so many cycle charges. So what you can do then is you open this auto darkening filter, you just connect the positive and negative, and I just connected a standard 3.7 LiPo battery. This one actually came out of an old laptop. This works incredibly well, and it keeps its charge for years. I mean, this helmet can be under a dark bench for months and months. Well, probably last time I used it was about a year ago, and I used it the other day and it is still perfect. So this is a worthwhile thing to do. If you don't want to do this and you want to leave the little 3.7 volt battery, no worries. Just before you weld, just go stick your helmet in the sun for an hour or two and you won't have any issues. These helmets are incredibly simple. You have the sensors on the sides, so just be mindful of that. If you cover the sensors with, if you're welding something and you cover a sensor, then it's not going to activate. So just make sure that these sensors are sort of open to where you're welding. Another thing with these helmets is these covers, the two plastic covers on the inside and on the outside, tend to get grimy because of the gases and all of that. So you do need to either replace them, or what you could do is you just take them off and you polish them and put them back. The single most important thing about a helmet and welding is getting a good view of your weld. If you can't see what you're welding, you're not going to be able to weld properly. The other things in the helmet are actually very, very simple. It just has a delay time, long and short, and I just put it on long, but it doesn't really matter. These delay times and sensitivity is more for if you're in a workshop with lots of other people welding. If you have a low sensitivity, typically if other people are striking arcs, you don't want the auto darkening helmet to sort of go light and dark all the time. So if you're in a workshop with lots of other welders, you just set it on low. In a home workshop where it's only you just set it on high and you leave it there. The delay time, I normally set it on long, because once you've struck an arc, you don't want it to flicker on and off all the time, because that kills the battery. So I set it on long, but if you're doing lots of short little welds, then leave the delay time on short. The shade for TIG welding on the amperage that we normally weld, I just set it to the lowest and then that's fine. If you're doing arc welding and stuff like that, you sort of need to push this up. And the higher the amps, the more shade you need, depending on how good your eyes are. This little helmet has lasted a long time. I'm very happy with it. Okay, so before we get into the nitty-gritty of welding this boiler together and all the sort of finer minutiae of welding, you do need to do all your bushes and stuff like that. And it needs to be the same stainless steel as the rest of the boiler. Remember in that first part of the boiler series, I spoke about the differential expansion at a specific joint and how dangerous that is to have dissimilar metals. So it needs to be the same material and same quality as the rest of the boiler. A little tip on tapping stainless steel. Most of the drill sizes for a specific tap that's written on the side of the tap are for 80 or 85% thread engagement. When you're tapping stainless steel, use a 60% thread engagement. So in other words, the tapping drill will be slightly bigger than the standard one. And what that does is it gives you a better thread, and it doesn't bugger up your taps, because stainless steel is not the easiest thing to tap. So yeah, just check that your drill size is for a 60 or 65 thread engagement. Then there's a couple of things you need to make for a boiler. The bigger roll things can be done in a large workshop, but the smaller stuff the guys won't do for you because they just won't be able to roll it. So you need to do this in your home workshop. And contrary to popular belief, it's actually very, very easy to form stainless steel. You can do it with a hammer around a bar. I normally go one step further and I'll roll it and then I'll squash it flat. This is specific for the fire door ring. And give yourself a little bit of gap in between the two for tolerances later up and for expansion and so forth like that. The other thing that you're going to run into sort of issues with stainless steel is cutting holes. Now, most of the holes are pre-cut with a laser cutting, but on the odd occasion, you're going to have to make a relatively large hole. And it is incredibly painful to make these large holes in a material like stainless. So here's a little trick. If you take a bandsaw blade, and I typically use one of my broken bandsaw blades, it's not worth putting together again, and you just cut a ring with a little spigot on, then you can weld it onto the back end of the bandsaw blade. And this is a very specific type of weld. This is called a fusion weld, and I use the same process for my tubes. It looks a little bit like this. If you take the welding torch, you put the welding torch on the one side, you actually collapse the weld onto the bandsaw blade and you get a fusion weld. So there's no filler rod in this specific weld. All you need to do is to make sure that you have a little guide at the bottom end. So you drill a pilot hole, then this guide goes into your pilot hole, and then you can cut relatively large holes on sort of materials that are not flat or round, for example, the boiler tube. This is much easier than sort of messing around with bored high-speed steel hole saws or stuff like that. The TIG welding torch is really just a collet system that allows gases to pass on the outside of your tungsten electrode. Now remember, the tungsten electrode doesn't disappear in the weld, or at least it shouldn't. But what you do is you create a weld pool with a non-sacrificial electrode, which is your tungsten electrode, and then you just fill it as you go along. The torch itself is really just the collet, and the tungsten rod goes on the inside, that goes into an outer collet, and this backing sort of screw thing just tightens that up against the outside collet, and it clamps the tungsten rod on the inside nice and neat. It is very, very important that when you set up your torch, the back end gets screwed out, and then you tighten your collet system by finger tight, and you'll see there's knurling on the outside of here to do that. So that gets tightened finger tight with a small gap there. You'll see that the tungsten rod on the inside is loose, and then when we tighten the back end, it nips it up nicely, and now this rod is tight. It is very important then that this tungsten rod on the inside of the collet is very tight, because at the end of the day, this is an electrical connection. So if it doesn't make a good connection, then this tends to run hot, very hot in fact, and you end up damaging your torch. So you do need to have a good connection between the tungsten rod and the copper. Then it is just your gas shield that gets turned in to finish the torch, like so. Then that is tightened perfectly. You get two types of backs. The one is where you can use the full tungsten rod and it sort of hides in the back there, or you get a shorter stumpy one to get into sort of small places. When you grind your tungsten rod, typically you look for about 3 times rod diameter from the point. So that sort of sharp point there is about 3 times the diameter of the rod. Anything more than a 1.6 millimeter rod, you need to sort of cap the tip off. And typically you take off about 1/4 to 1/2 of this rod diameter. So for a 2.4 millimeter rod, you divide it by 1/4 or 1/2, and then that's how much you take off of the point. But again, the length when you're grinding it is 3 times the diameter of your rod. When you're grinding the tungsten rod, it needs to be in the same direction as your grinding wheel. So in other words, all the grinding marks are in this direction. The reason for this is if you do it in the opposite direction, so your grinding marks are in sort of this orientation, you end up with a very unstable arc. So if these are in the direction of your grinding wheel, your arc is stable and you won't have any issues. The size of the cup is to a large degree dependent on the size of the electrode, and that there's charts for on the internet. As a starting point, the 1 millimeter rod, you use a 4 millimeter cup, the 1.65, and then the 2.4 is the next size up, 6. The length that the electrode should stick out of the cup is roughly the radius of the cup. So if you have a look at this electrode, the middle of the electrode from there to there is roughly the same that it's sticking out. And if you're in a no draft area, you can go a little bit more if needs be. And typically you would do that if you need to get into a corner. Okay, so I promised to give you guys a rundown of this very cool welding machine and what all the different settings do. And it's quite simple, so we can run through it very quickly. If you have a look between the knobs, there's a curve here, and this curve tells the whole welding story. But before we get there, let's just have a look at these switches on the side. 2T and 4T has got to do with the amount of times you press the welding gun button. So if you have a 2T, you press, you hold, and then you weld like normal. That's a standard sort of way of welding. The 4T is typically used when you do long welding runs. So you press the button, you weld, and you can let go of the button, you weld, and you press it again, and then you'll stop your welding. But for the average home workshop, 2T is good enough. This welder has a MMA and a TIG welding setting. The MMA is for stick welding, and the arc force, this button over here, is just for your stick welding. So all that does is it gives you a peak current when you weld, and that's just so that your welding stick doesn't stick when you weld with stick welding. I have no idea why they bother putting MMA on these machines, because it's a TIG welding machine like this is typically used for TIG and very, very seldom used for stick welding. Then when we get to the TIG welding, these machines have a pre-flow and a gas afterflow, and all that does is it keeps the weld route clean when you start and when you end your weld. Most of the weld inclusions or sensitivity of the welds happen when you start and end your welds, and it's normally that very aggressive arc strike when you have a more oxidizing environment around your molten metal that you end up with a problem. So the whole idea of these pre and post gas flow is to flood the area with argon gas so that you don't get that initial porosity or initial oxidization of your weld. Similar idea with the downslope, and some machines have got an upslope. I haven't got an upslope on my machine, but all that does is it ramps down your amperage on a curve so that you don't have a very aggressive first arc strike. Now for standard TIG DC electrode negative welding, which is your standard run-of-the-mill welding, all that you do is you set everything to 0, and then you just work on a peak current of whatever you're looking for. There, in a case like this, if your machine hasn't got the pre-flow and the downslope and all of that, and you only have an inverter welder, this is the setting that you are basically welding at. You have a peak current and nothing else. Now there are ways to not have a problem with the beginning and ending of your welding, and that's just, there's a couple of tricks that you can do there. Okay, so let's say that we have a material like stainless steel, a material that has a high melting point, but it has a low conductivity. And of course, it has a major problem with distortion because of the heat input. This machine, what it can do is it can have a peak current. You can set a frequency, you can set a basic current, and a pulse width and a pulse duty. Now, all that you are doing there, and it sounds very fancy and very complex, but think of it like this. You are welding at a very high temperature. That arc temperature is about 2000 degrees C plus. Your melting point of stainless steel is about 1500 degrees C. You're welding on a temperature. You only need a certain amount of heat flux input to get a weld pool. So what you can do is you can set a DC pulse with a pulse frequency. You can set a basic current, let's say 50% on my machine, and then what you're basically doing is the area under the curve is far less than if you were welding just DC straight negative. So your overall heat input into your weld is far less than if you were welding just DC straight negative. The pulse frequency has an added benefit. The higher the pulse frequency, the more the arc sort of narrows. So your heat input actually narrows into your weld pool area. So you end up with a much narrower weld pool, and you penetrate your base metal a lot more. Your pulse duty on these machines just shifts the time that your peak current is, or your base current is active. And the higher you go with your pulse duty, the more you're at your peak current. So again, what it does there is it just increases the time, or increases the amount of heat that you're putting into the material that you're welding. Now let's think about this practically, right? If you're welding stainless steel, as I mentioned, you've got a high temperature arc, You don't need as much heat input because the material doesn't get rid of the heat as quickly because it's lower conductivity. So you can get away with quite an aggressive pulse frequency with a 50% pulse duty, a peak current, and then a basic current of, let's say, half. And you're going to halve your heat input into your weld. But let's take another material like copper, for example. Copper's got a much lower melting point. It melts at about, say, 1090 degrees, depending on certain conditions. But conductivity of copper is much, much, much higher than stainless steel. So everyone knows that you can't weld copper at 60 amps. It just won't work. You won't get a weld pull. You need to do two things. You need to preheat, and you need to have all the weld inputs. In other words, you can't have a basic current. You need to set that to 0, and you need to have a DC current. So then your pulse frequency and your pulse duty aren't helping you at all. So basically, you're putting as much heat as you can into that weld pool. Okay, so nearly all of these machines can weld aluminium. And the problem with aluminium is the oxide layer. So if you think of a welding torch, the electrons go from the electrode to the workpiece, and there's a energy transfer from the welding into the workpiece. When you're welding AC, the electrons go from positive to negative, and that's different to the DC pulse welding. You see, the DC pulse welding is always in one direction. The AC changes direction, and what that does is it strips that oxide layer off of the material. So materials like aluminium with that oxide layer, you typically weld AC, and then that cleans that oxide layer off of the material. The cleaning area width is just how much distribution you have between the positive and the negative. The higher the cleaning width, the more energy you're taking away from the material, so the more that you're stripping that oxides off of the base material, but the more energy is going into the tungsten electrode, so that the tungsten electrode gets hotter. That's why when you weld aluminium, you do need a thicker tungsten rod just to manage that extra heat transfer. Another thing you need to do with AC welding, and specifically with aluminium, is you do need a foot pedal. Reason being is your first strike is typically a much hotter strike, and then you can push back as the material heats up. An interesting point on the pedal, if you're doing highly specialized welding with, say for argument's sake, boilers with the stainless steel, there's a welding qualification that you need to do, and that's that WPS that I showed you right at the beginning of the video. If you weld with a foot pedal, you don't actually know what current you're welding at. It could be your maximum setting or somewhere between your base and your maximum setting. So you would very seldom walk into a welding shop where they're doing qualified welding procedures with a foot pedal. Typically, they stay away from the foot pedal just because you never know where you are with your welding. And engineers don't like welding if you don't have the very specific amps that they specified, and rightly so. All right, let's finally get down to some welding. It's very, very simple. Normally the filler rod goes in between your fingers and you feed with your thumb. So backwards and forwards. The welding gun sits at about 30 to 40 degrees from your weld root, and you feed in about 15 degrees. You strike an arc and you feed in one direction, and you dip the welding rod just in front in your weld pool, like so. Alright, so the weld has cooled down nicely. I have a beginning and an end of the weld, so that will become part of the test. Got a nice wavy nature, so that looks pretty good. There's no collapsing of the outside of the weld, and a little bit of over penetration, but I can live with that for a 3mm plate. So this will be my setting for the rest of the boiler. Now, this test piece over here will be tested to destruction in the vise, and then this will be given to the boiler inspector. Now you can see this is a stainless steel weld. I'm bending it on itself, and you can see this weld hasn't cracked at all. So that means this weld is ductile, it's good. I'm very happy with this. So this will be marked with the date, and it will become part of the boiler pack. But now I can start welding the boiler, which will be the next part.